Hello, I'm Seema and welcome to part 3 of the topic Acids and Bases in Organic Chemistry. In this video, we are going to continue our discussion about the mnemonic that we used, CARIO. And this mnemonic, CARIO, stands for 5 steps that we use to identify and to compare the acidic and basic strengths of compounds. In the previous video, we discussed charge, the charge of the acid and the charge on the conjugate base, and compare the conjugate bases and the acids and on the basis of the charge. In this video, we are going to study about the second step, that is the atom holding the charge. Many a times when we are comparing the acids, we find that all the acids, they appear to be having the same charge, or all the conjugate bases also appear to have the same charge. If they have the same charge, then how would we compare their acidic strength if we do not know their Ka or pKa values? So the second step is to now focus on the atom which is losing that hydrogen. On deprotonation, that is on the loss of that hydrogen ion, it is the atom which loses the hydrogen ion. We have to turn our focus towards that atom now. Instead of seeing the whole species, that is the charge on the whole acid or charge on the whole conjugate base, we now focus on that one atom. So let us take a few examples here and see what happens when we focus on that atom. If you remember, the previous topic that we did was the periodic table. And in the periodic table, we noticed the trends in a periodic table, that as you move from left to right in the periodic table in a period, the electronegativity increases. That is, the tendency to gain an electron or the tendency to pull a shared pair of electrons towards itself for an atom increases. And as we move from top to bottom in a group, the size of an atom increases. These are the two trends that are going to be relevant with this step. That is, when we are looking at the atom. It is these two trends that we have to keep in mind when we compare these these molecules. Now, in every example or every reaction that I have taken, I've chosen these 5 problems. I have written the entire equation of the deprotonation. That is the acid, the loss of the proton and the conjugate base that it produces. And then I would like to start from there. This is the first question in which we have been given 4 acids. One is methane, ammonia, water and hydrogen fluoride. These are the 4 acids that we have, and I've written them in a way so that you know the structure, and on deprotonation it is this hydrogen which is leaving, and in this case it is this hydrogen which is leaving, which is being lost since it's an acid. So when methane loses the proton, we find that it forms CH3. And when the proton is lost, this hydrogen is lost, it loses its electron and leaves. When it loses its electron and leaves, it is positively charged. Therefore, these 2 electrons of the bond now belong to carbon. One electron which already belonged to carbon, but 1 electron of hydrogen has been added to the carbon. Therefore, a negative charge is seen on the carbon. Right? So we notice this. Now, when we take ammonia and deprotonation occurs, we find the negative charge on nitrogen, we find a negative charge on oxygen in the deprotonation of water, and we find a negative charge on fluorine in the deprotonation of hydrogen fluoride. Now, if we were to compare the charges, we find that all 4 have the same charge. All 4 acids were neutral, and all 4 conjugate bases have the same charge. Now, how do we compare them? So now we look at this atom, the atom which allows the hydrogen to be lost. So it is not the proton which is lost which should be our focus, rather the atom which is losing that proton, we start focusing on that. So we find that carbon, nitrogen, oxygen, fluorine, carbon, nitrogen, oxygen, fluorine, they belong to the second period in the same sequence. I've deliberately written the same sequence here. Right? So carbon, nitrogen, oxygen, fluorine. So as we move from left to right, electronegativity increases. That is, fluorine would be the most electronegative and carbon would be the least electronegative. Now, an electronegative atom should have a greater tendency to pull the electrons towards itself. Therefore, when fluoride ion is formed, this would be more stable because it has a stronger tendency to pull the electron towards itself. While carbon has the least, it doesn't want to pull electrons towards itself, yet we are forcing that electron on it. So the methyl ion as such would be unstable, but the fluoride ion would be the most stable. And you remember, what did I tell you? On the basis of stability, the conjugate base that is stable means the acid, if it is stable, it means that it will not react. It is a weak base. If it's a weak base, the acid should be a strong acid. So we say that fluoride here is the most stable ion and methyl ion here is the least stable. So this conjugate base is the weakest base. It is the weakest base, and this then would be the strongest base. And we follow the sequence. Now, if this is the strongest base, this comes strongest, then less than that, then less than that, and this is the least strong as a base. So the acid would follow the opposite. The weakest base would be the strongest. The acid, for a conjugate base which is the weakest base, the acid would be the strongest. So HF would be the strongest acid, while methane would be the weakest acid. I hope I'm clear. Now, what did we do? As we move from left to right, electronegativity increases, and therefore the atom which is to the extreme right, which is most electronegative, will form the most stable base. And if it will form the most stable base, it will have no tendency to react with the hydrogen ion again to reform the acid, and hence in the equilibrium equation the dissociation of HF would be the most. I've made only one arrow. There should be equilibrium in all the cases. So HF, the tendency to reform HF would be the least, and hence the hydrogen ion concentration here would be the highest, and in this equation it would be the least. So this is the weakest acid and this is the strongest acid. This is the strongest base and this is the weakest base. So now let us come to the next problem here. This is ethanol, and when ethanol protonation occurs, we are left with this ion here. The oxygen is the atom that we are concerned with, O negative. In ethanamine, again, it is this nitrogen which has the negative charge of the conjugate base. And this is ethane. And on deprotonation of ethane, we get this ion where the negative charge is on carbon. So again, it is the same factor that comes into play. What are the three elements we have? Carbon, nitrogen, oxygen. So in the period, carbon, nitrogen, oxygen are in this sequence. So which is most electronegative? Oxygen. All three, I would like you to notice that all three have a single negative charge. So we cannot use charge to compare these acids and bases. So carbon, nitrogen, oxygen, as we move in a period, oxygen is most electronegative. The most electronegative will be the weakest base. If this is the weakest base, this would be the strongest acid. And this would be the weakest acid, while this is the strongest base, or the most unstable, and this is the most stable ion. Right? Stability and basicity, the trends are absolutely opposite. The most stable would be the weakest base, and the most unstable would be the strongest base. Right? So now let us come to this next problem. HOH forms OH negative, and HSH, that is H2S, forms SH negative. Right? The negatives are on the oxygen and sulfur. Again, both oxygen and sulfur belong to the 16th group. They are in the same group. Oxygen is in the second period while sulfur is in the third period. The size of a sulfur atom is larger and the size of oxygen is smaller. Now, how does this affect the acidity or the basicity? Let us just observe. I'll just give you an example, an imagination. I have a nice, beautiful Tesla car, and I have to transport it from one place to the other, and it is not possible. It's brand new and I do not want to drive it yet because I want to take it on its first drive on a special occasion. So I want to have it delivered to me in another vehicle. So when I do that, I choose a vehicle which is smaller than the size of a Tesla, and it has a carrier that has a smaller size than a Tesla. And if I put my Tesla over it, which is so very precious to me, imagine what would happen. The weight of the Tesla would fall on a smaller body, and the smaller body would have a tough time picking the Tesla up. But if I have a big, huge lorry, and in the lorry there's enough space for a Tesla to drive in and there's enough space for another 6 cars to come in, would that not be better? Because if I have a larger lorry, now my Tesla can comfortably drive into it, go into it, and now it sits there, and the lorry has a much larger space, the surface area at the bottom, and therefore the weight of the Tesla is being distributed much better in the lorry and it is much more stable. But on the other hand, when I had that little tractor which had a small little carrier on which I had put the Tesla would be very uncomfortable, and the little trolley would have a tough time pulling the Tesla under. The Tesla would be very unstable and there would be chances of the Tesla falling off. Now imagine that oxygen is a very small atom. And when this electron, on deprotonation, when hydrogen leaves and it leaves without its electron, it pushes that electron over to oxygen. And when oxygen has that electron over itself, it is like that little trolley which has so many electrons, and the weight that has to be distributed or the charge that has to be distributed is in a very little space, and therefore there would be repulsion, there would be instability. On the other hand, sulfur is like that lorry which is carrying your Tesla. It's huge and the Tesla can easily drive over it. So the electron that comes, there's enough space for all the electrons to peacefully coexist without really repelling each other. Because there is that much of space around it, the HS negative or SH negative ion would be more stable. Right? SH negative would be more stable, while OH negative would be less stable. So what does stability tell us? If this is more stable, it means it would not react back to form the H2S. Therefore, this is a weak base, less reactive base, while this is a strong base. So anything that has a strong conjugate base should be a weak acid, and one that has a weak base should be the stronger acid. Right? So we see in water and H2S, H2S would be a stronger acid and water would be a weaker acid, because H2S would form a more stable conjugate base, which means a weaker base. Right? So now these were 3 problems. Let us now move on to the 4th problem here. We have 4 acids: HF, HCl, HBr and HI. On deprotonation, they form the chloride ion, chloride ion, bromide ion and iodide ion. All of these have a single negative charge. Therefore, in CARIO, we do not use the first step. We move on to the next step, the atom bearing the which is holding the charge, or the atom which loses the proton. So compare fluorine, chlorine, bromine, iodine. All four of them belong to the 17th group of the periodic table, and as we go down the group, the size of the atom increases, and as size of the atom increases, the lorry and the small little trolley, you have to remember. So this is the lorry and this is on the small little trolley. The electrons are on the lorry, electrons on the trolley. So the ones that are on the lorry are stable. This is the least stable. And this is the sequence of stability. Stability is increasing downwards, and therefore basicity would be the opposite sequence. So what would the basicity be? The basicity of iodide ion, if this is stable, it means it is least basic. This becomes a stronger base, and this is the most basic. And if it has the most basic conjugate base, the acid would be the least acidic. And Hi would be the strongest acid. Right? This is the strongest acid and this is the weakest acid. That would be the sequence. Let us now just deal with one last problem, and then we would be, in the next video, we'll be able to move on to the next step. That is resonance. Now here we have NH3, ammonia. And on deprotonation, it produces NH2 and the negative charge is on nitrogen. And we have H2S, where on deprotonation, it forms SH negative. Both have a single negative charge. But if you now want to compare the second step, that is atom, and we go along a period and we go along the group, neither do the two elements here belong to the same period, nor do they belong to the same group. So now what do? We just check where their positions are in the periodic table. We find that nitrogen, after nitrogen is oxygen, and sulfur is below oxygen, right? This is the 15th group, 16th, and both of these are in the 16th group. Second period, third period. So it means that nitrogen, if you move from left to right, that is from nitrogen to oxygen, now we see that oxygen is more electronegative than nitrogen. So oxygen, if it is present if it is the atom which is bearing the charge, it should be more stable base. If it is more electronegative, it should be more stable base. And as you go down, the size of the atom increases. Therefore, an atom bearing the charge on sulfur, that is sulfur HS negative, this should be more stable, right? We notice that in comparison to nitrogen, oxygen should be more stable, and in comparison to oxygen, sulfur should be more stable if it is bearing the charge. So what do you deduce from this? Oxygen, a conjugate base having oxygen is more stable than a conjugate base having nitrogen. Yes? And a conjugate base having sulfur is more stable than oxygen. So if you just remove this oxygen from the middle, we find that sulfur, a conjugate base having sulfur, is more stable than nitrogen, a conjugate base having nitrogen. So SH negative is more stable, right? And NH2 negative is less stable. If it is less stable, it's a stronger base. And if it is more stable, it's a weaker base. And the acid strength would be according to this now. So if it's the weaker base, this is the stronger acid. And since this is the stronger base, out of these two, this is the weaker acid. Right? So this is how we use the atom, the second step, the atom holding the charge, to compare the acidic or basic strengths in organic compounds, or basically all acids and bases. So if you found this video helpful, please give it a thumbs up and subscribe to my channel and recommend it to your friends, and please keep returning for more videos in chemistry. Thank you and bye-bye.